this session we've got two speakers before lunch. And first up, we've got Alexandra Stralova from Newcastle University.
Thank you, Richard. So today I'm going to talk to you about my research in emulating deterioration of infrastructure assets. So this is quite a relevant topic these days because of climate change and rain in the UK and Victorian infrastructure in the UK. These three things come together to create the perfect disaster, which is crumbling rail infrastructure. Well, some of it is crumbling, some of it is not. I work as part of the Achilles Consortium here, which is a big research grant. It's coming to an end this December, so we're rounding up all of the research that we're doing, and some of the things that I will mention today will be hopefully published very soon, hopefully submitted very soon. None of this would be possible if it wasn't for my fabulous collaborators. Peter Helm here is the numerical modeler. Dennis, Mohammed, and Stephanie and Darren are my more senior colleagues, and Jordan Oakley is a postdoc, which has recently come under my influence. So there we go. So a bit of background. Deterioration of infrastructure slopes in the UK is a very important and significant topic to think about. Many rail slopes in the UK are about 200 years old, so they're sort of Victorian time. And we will be looking at the infrastructure which is in the south of the UK, because it is built in high plasticity soils. Some of these soils are clays, and the one that we look at is called London clay. And because of the weather, the deterioration is increased. So there's normal wear and tear due to weather because we have warmer summers and wetter winters, and this cycle of wetting and drying will cause deterioration of these clay-like soils. But because of climate change and because of increasingly drier summers and because of increasingly wetter winters, we have more disasters that look like this. So this is a landslide on a rail line between London and South Wales, and it was quite bad. I'm just going to move this. Highways suffer similar problems, but because they're younger, the problems are not quite so severe. And our focus is the Great Western Main Line, which is this section of rail between London to Bristol. We'll look at this part of rail infrastructure because it's one of the most highly used. It has a lot of loading, it's got a lot of passengers, so it's quite important that we look at it. Now, I'm just going to show you the variety of the soils, different types of soils in this rail corridor. So if you look at this line here, we have different failure potentials here. So we have something which is sort of medium to low failure potential. We have low potential. I'm sorry, I can keep hearing myself. Low failure potential, and we're looking at this high failure potential, which comprises a big... do you mind if I switch the microphones? It's a bit... I can hear myself. Oh, it's the second one. No, it's this one. Is this better? Oh, this is much better. Good. So, yeah, this significant section in the middle of the London to Bristol corridor is a high failure potential section, which is not great. And also some bits towards London are quite high failure potential. So that's not great. So deterioration can be studied through computer experiments. It can also be studied through actual laboratory experiments. You can set up infrastructure labs. You can set up sort of model infrastructure, but it's very expensive. So instead, you study deterioration through computer experiments. But similarly to the previous talk, these computer experiments are expensive. They probably won't cost millions and billions of computer CPU time, but they still will take years. So the particular thing that we're studying is the strain softening of over-consolidated clays. And these over-consolidated clays are basically the high failure potential soils that I told you about. They're highly influenced by wetting and drying, so we're really interested in those. And we created a training data set of just 76 experiments, which took us maybe 2 months to evaluate. And we'll be applying Gaussian processes to this, and I'll go into details of how exactly we're applying Gaussian process. But the main task of this exercise is to relate the inputs to the outputs. The outputs in this case are some measures of deterioration, which can be time to failure of an infrastructure slope, it can be deterioration curve of an infrastructure slope, or it can be the amount of failure that failed of an infrastructure slope. So we are trying to relate these failure outcomes to the inputs which characterize these slopes, which include slope geometry, so how steep or big it is, the type of soil that is built in, and also permeability. And permeability is how wet the soil can get effectively. Wettability. It's not quite wettability, but it relates to how wet an infrastructure slope can be. So something that we've already done is monitoring time to failure, which I will be focusing on. So it's not a particularly difficult thing to emulate, but because it was my first research project in Gaussian processes, I sort of looked into a lot of detail relating to that, so I'll show you that. Our current work is modeling factor of safety, which is a deterioration curve, which I will mention briefly. Just as a comparison, this is sort of efficiency gains that we're looking at. So the numerical model takes 10 machines and 40 days to evaluate 76 models. And the emulator, once it's trained, which is an important asterisk, once it's trained, it can train up to 1,000 models in 5 hours on just my machine. So that's all good. And that's a fully Bayesian emulator. That's not an optimized emulator. That's a Bayesian optimized emulator. Okay. I assume you've seen how to define a Gaussian process many a time this week. So apologies if some of this is repeated, but I'll go through the very basics and we'll dwell on the details which I find interesting. So the emulation problem is to think of the process that you're emulating as a function f, and then you require some other function which approximates f. So this function is called eta, and we use Gaussian processes. So you train eta using the evaluations of the true model that you're interested in. F needs to be smooth and continuous, which is fine because deterioration process can be modeled by differential equations, so it is smooth. Also, if just a bit of background, the word emulator was coined by Tony O'Hagan. So emulator is just not any surrogate model. It's an emulator because it takes a full account of the uncertainty about the process that we're emulating. And I saw a talk at one of the earlier summer Gaussian schools, and Tony was quite adamant that an emulator is not just any simulator, and it's a simulator which takes the full account of the uncertainty. So there we go. Now this is how the Gaussian process is formally defined. This function takes some inputs, which can be many-dimensional, and Gaussian process is defined on using a mean function and a covariance function, which is m and v, and it needs these hyperparameters. So I will talk a little bit about the mean function. The mean function, I think, from what I've read in the literature, is the things which can be most underused. Because the mean function can work as a regression in your case, or it can be any other function. So if you believe that you have some inputs and you have some outputs, and that these inputs and outputs are related in some non-ambiguous way, you can include this belief in this mean function. In our case, it's a linear transformation of the inputs. So for example, time to failure is related to how high an earthwork is. The higher the earthwork, the lower time to failure, for example. Or there's the stronger the earthwork, the longer the time to failure. Or maybe there is an interaction effect between the strength and the height, and you can include this interaction effect between the strength and the height. In this mean function, you just include an interaction term like in any other linear regression. Then we have this variance function, which is defined as this marginal variance and the covariance function and some nugget. So this noise can either account for the uncertainty in your measurements, if you believe that your measurements or the outputs of a numerical model are non-deterministic, you set this guy, this nugget here, to account for that noise. It's also useful for numerical calculations, so if it's difficult to invert this function here, then you can add a little number to the diagonal of this matrix to improve inversion properties. And this correlation function is what we've been working a lot with one of my PhD students who's in the audience. So we've been working on some process which is basically some weather data. Weather data has a trend, it has some seasonality, and it has some noise. So you can include features of your process, not just in the mean function, but in the covariance function. These guys are just the vanilla options. You've probably seen them this week. You've got your Gaussian function, you've got your return covariance function. Also, if you haven't realized, these two things are basically the same, except the Gaussian function is infinitely smooth, and the return function is as smooth as you want it to be. You can control how many times you can differentiate it, and the Gaussian correlation function is the limit of the return function when the smoothness is infinite. But let's go back to that weather example. If you believe that your data has not just one dominant behavior, it has a number of dominant behaviors, you can simply sum these covariance functions together. So you can have a function characterizing the trend, plus function characterizing the seasonality, plus a function characterizing the noise. So this is really quite powerful. And all of these parameters need to be tuned, and since I'm a statistician, since I'm a serious statistician, I'm going to be Bayesian because I can. This is where the magic happens. So if you know this bit of multivariate normal theory, you can write out your Gaussian process emulator. You've probably seen this before. And this is just a mathematical equation describing a Gaussian process conditioned on the observations. So can I just have a raise of hands if you've seen this earlier this week? Okay, good. So some people have, some people haven't, which means I can talk about it. This is great. So to train, let's go back. As I've said before, Gaussian process is defined by the mean and the variance. And if you're confused about the difference between a Gaussian process and a multivariate normal distribution, you shouldn't be, because a Gaussian process is basically a limit of the multivariate normal distribution, which is infinite dimensional. So within an interval, you just assume that you can have infinitely many points, which is the case with any continuous data. So if you want to model a whole interval, which is continuous, you would use a Gaussian process. But if you have discrete data, use a multivariate normal distribution, or if you have a discrete process. But since no computer can ever evaluate infinite dimensional data, in practice, all Gaussian processes become normal distributions, multivariate normal distributions, computationally. Mathematically, it's important to remember the difference, but computationally, it's always a multivariate normal distribution. So anyway, we need to assume that our emulator is a Gaussian process. We need to assume that the training data follows a normal distribution. So we have also our training data Y follows a normal distribution. This is our regressor matrix. So as I said before, we assume that our mean is a regression, and that's how you write it out. You have a regressor matrix, you have some coefficients, and then we have some variance. And then the Gaussian process, conditional on the data, is still a Gaussian process. Hey, this is great because we can write it out. You don't need to write an optimization scheme just for this process. To tune the parameters, you need an optimization scheme, but not the analytical form, which is great. It's not always the case in reality. In fact, it's very rarely the case. So this conditional Gaussian process has a mean, which is this guy, and has a variance, which is this. So this mean is the initial mean, plus some scaled error term. So this is the observations, this is the mean of the observations, and this becomes the error, and this error is scaled. So this is the mean of a conditional Gaussian process. And then if you look at the variance, well, the variance is the same as the initial variance, except it's smaller than the initial variance because you have these observations here. So this is a covariance term, and this is the inverse variance of the observations. So the takeaway is, the more data you have, the more certain you are in your Gaussian process prediction, because of that equation, that your variance decreases, the more observations you have. Okay. And this is another thing which is neat. So has anybody in the audience worked with missing observations or with censored observations? Yes. Did you know that you can estimate them using Gaussian process? Yes, we can. So what you end up doing is quite neat. You partition your process, and this is just for censored observations. You partition your process into a Gaussian process which corresponds to the data you have available and to the data you don't have available, but which is censored. And censoring is not the same as missing information because the censoring limit tells you that something is within a certain limit, but nothing more. So in this case, we have a lower limit here. So we know this is true for deterioration because we know we have a certain amount of weather data, so we simulate deterioration for about 200 years. And after 200 years, if an earthwork hasn't failed, it hasn't failed. And that's all we know. So we have censored data. So this censored data becomes conditional on the observed data. And it's also a normal distribution, except now it's just a truncated normal distribution. So you just have a lower limit for us. And this is super convenient, super convenient. Give me one moment whilst I try to switch that thing off. I can mute it. I can just mute it. Oh, there we go. I've muted it. Oh, good, thank you. Have I? Maybe. Right. Any questions so far? No. So unfortunately, this conditional form, even though we have it, because none of these parameters, rewind. So I optimize the parameters using Bayesian inference. And that means that we have some likelihood corresponding to the model. We have some prior distributions corresponding to these parameters, which are expert beliefs about, for example, the regression coefficients. So if we want to relate the height of an earthwork to time to failure, we do it through this regressor mean. And then we need some prior distribution on the coefficient associated with this. So for example, I need to go to the engineer to sit him down, make him a cup of coffee and say, what do you think is the relationship between the height of the earthwork and the time to failure? And we try to put it into a prior distribution. So this prior distribution becomes a certain mean, for example, and a certain range of uncertainty. And this is known as prior elicitation, and that's what we spend an awful amount of time on. So when we're being Bayesian, unfortunately, we can't quite use this form to obtain our emulator. But we can use it within an MCMC scheme. So if you're interested about how to use this kind of approach in an MCMC scheme, I can tell you. Otherwise, for now, I won't, because it will take a long time. Yeah, so but before we start the optimization, we have to set these prior coefficients. If you want to be lazy and don't want to speak, or want to be unsociable and don't want to speak to your engineer, you just set vaguely wide priors to the regressor coefficients like I did here. So the regressor coefficients have a super wide range of uncertainty, which was actually quite unhelpful. But because the Gaussian process itself fitted quite well in our case, it didn't matter. So when I show you the results look very plausible. The predictions have about 80% of accuracy. So actually, I got away with this in the simple case. In the complicated case, you don't get away with this. So yeah, we use MCMC, Metropolis and Gibbs scheme, and then we've looked at different mean functions and different covariance functions, which I will show you. So before I get into results, this is our Larson hypercube design. So we had 76 experiments. This is the geometry array of the infrastructure slopes. This is the relationship between the slope angle cotangent and the slope height. It's in this triangular shape because anything above that sort of envelope will become an overhanging earthwork, which is implausible. So it's in this triangular shape. We also made sure that this geometry array broadly corresponds to published information on rail cuttings and highway cuttings. So that's that. And then we had some ranges for the height, angle, and then we had two strength parameters. One is known as cohesion, and the other is known as friction. And the final input is permeability. Anyway, they're just the input parameters that the engineers said will most highly affect deterioration. And now this was sort of in the middle of work in progress when we were trying to decide which covariance function is the best and which mean function is the best. So these are times to failure maps. We have some quicker times to failure, which are in red. We have much longer times to failure, which are in green and blue, and everything else is in between. So across the rows, we have different mean functions. So the top row is what you get in a black box Gaussian process scheme, which is a zero mean. There is no information in the mean. This is what will be fitted. The next one is slightly more complicated. It's just a non-zero mean. It's a constant. It's an intercept. And the final row is the regressive function mean. So let's just look at the rows at the moment. We'll go through the columns in a minute. We can see that the problem with the zero mean Gaussian process is that it's radial. There's no engineering reason why time to failure should be radially related to height and angle. There is no reason at all. But when we look at the regressive function mean, the change is now linear. And this makes perfect sense that as the cot of the angle increases, which means that the angle in degrees decreases, and as height increases, this change is linear. So the steeper and larger earthworks fail more quickly, and the more shallow earthworks fail more slowly. That makes sense. And now across columns, we have the three different covariance functions. And in this case, actually, so the Gaussian covariance function is the smoothest. Matern 3/2 is the least smooth, and Matern 5/2 is sort of in the middle. Visually, there's no difference. We did make a validation exercise, and we found out that actually the middle case, Matern 5/2 covariance function, was the best because it's not too rough and not too smooth. But but the gains in accuracy were 0.1% or maybe a couple of percent, so it wasn't dramatic. There was something else which created much more dramatic difference, which is output transformation. So when you use Gaussian processes for your emulation exercise, you have to think about what is the range of support for the numbers of your output. If they are strictly positive, for example, time to failure is strictly positive, you have to model, for example, the square root of the output or a log of the output or another function of the output, which then becomes supported on the entire real line, because Gaussian processes are supported on the entire real line. You can chop off Gaussian processes, so you can truncate them, but I wouldn't advise this because it's more difficult to code up, and it has some other inconvenient properties. So again, when you apply Gaussian processes, make sure it's reasonable. Right. Okay, so after we were happy, we ended up choosing Gaussian process with a Matern 5/2 covariance function and with a linear regressive function. And now we have certain time to failure maps for the different soil scenarios. So the 4 plots on the left, we have four soil scenarios. We have low strength, high strength, and 2 London clay parameterizations, which are what we're interested in and what is consistent with the literature. And we were happy to see that as strength increases, times to failure also increase, and as strength decreases, times to failure also decrease. And now this third column here is LiDAR data from the London to Bristol corridor. So these dots represent actual geometries on the London to Bristol corridor. And we've made the prediction for those. And then we compared our predictions with the results from our industrial colleagues. And the results from our industrial colleagues are these failure potentials. And they have 3 categories of failure potentials, which include low failure potential, medium failure potential, and high failure potential. And you can see that they actually align really well with our contours of time to failure. And I didn't choose the colors for them to agree well. They just happen to agree. And you can see that even this envelope agrees quite well. So that was nice. Right. Any questions at this point? Okay. And then we've done some sensitivity analysis. So we've used Saltelli style sensitivity indices, and we've also used these main effects. And the main effects is the average change of in the output as you change one of the inputs. It's defined like this. And because we're being fully Bayesian, we can actually obtain the ranges for these main effects. We can obtain a whole distribution of the main effects. It takes a bit of coding, but you can do this. So you'll basically get a curve or a line which shows how your output changes with your input. And then we have two other sensitivity indices. Have you seen the sensitivity indices earlier in the course? No. Okay, so without going into the equations, if you're interested in how these sensitivity indices are defined, these are the references. I can tell you later. So the first order sensitivity index is describing how the variance of the output changes with the change in a particular input. So for example, if I changed earthwork height, how much of variation in the output does that explain? And then there's this total sensitivity index. The difference between the first order sensitivity index and the total sensitivity index is that if you think of the regression, you can have different interactions between the different variables. So this total sensitivity index measures the variation of a particular input variable with all of the interactions. So when you compare the first order sensitivity index to the total sensitivity index, you'll get a feel about whether any of the variable interactions explain the variability in the output. So they can be quite useful. And the large difference between the two would imply that you have a lot of interaction effects. So this is our sensitivity analysis. On plot A, we have the main effects, and we can see that the strongest contribution to the output is the cotangent of the angle. So the more you vary the steepness of an earthwork, the more it will affect time to failure. So here, as cot of the angle increases, time to failure also increases, which makes sense. So cot of the angle is proportionately related to angle in degrees. Oh, sorry. And then we have some quite strong interaction effects from height and permeability, but they're much flatter. And then cohesion and friction are also flatter. So there we go. And then we have our sensitivity indices. So the first order sensitivity index is in red and the total sensitivity index is in blue. And we can see that, again, cot of the angle explains most of the variability in the output. And we can see that there are some interaction effects, but they're not dramatic. So the interactions in this case are not too strong. The next strongest variable is height. And then the other 3 variables are not as don't contribute as much to explaining variability in the output, which was interesting because we picked these input variables on the advice of the engineers. So we went with them. But looking at the sensitivity analysis, it's actually, quarter of the angle is very important, but the others are not quite as important. Right. Another thing we applied a Gaussian process simulation to is the failure area. And now, even though we still had a linear regressor function, this map is no longer linear. You've got a lot of different things going on. So let's go through this slowly. We still have the geometry array, and we still have quarter of the angle and height in the plot. But now we have these dots here. So these dots explain modes of failure. Cutting infrastructure slopes can fail. Either they can have a landslide, or their base can fail. So there are two main different modes of failure. And then, And then when we have a landslide, we call it a shallow failure, which are the sort of brighter dots. And we have a base failure, we call it a deep failure, which are the darker dots. And without going too much into detail, you can see that there's this envelope between shallow and deep failure, which is here. So these were characterized by an engineer without seeing any of my outputs at all. And you can see that actually the contours of failure area material follow these modes of failure, which was quite nice. So especially for the London clay type soils, you can see that there are some contours of failure material here. And these failure modes follow this quite well. Does that make sense? Roughly? Okay. Right. I will go in a little bit into the work that we're currently doing. Because it's unpublished, I won't go through it in detail, but I will sort of tease the problem. So the problem is this factor of safety curves. Factor of safety is a measure of deterioration. It's related to strain and stress of earthworks. And in very basic terms, a factor of safety of 1 means engineering failure. You probably will get operational failure in different circumstances. Sometimes operational failure can happen on a really, really poor earthwork. Sometimes operational failure, such as a speed restriction, can happen in very safe engineering conditions, but for some reason there's operational failure, like leaves on track. I mean, it doesn't really damage the earthwork to have leaves on track, but it's an operational failure. So there we go. Anyway, factor of safety curves, they are really heterogeneous, really heterogeneous. So there's different ways you can use Gaussian process to model this kind of a problem. You can have a dynamical Gaussian process where at every time point you have a Gaussian process. So every time, the distribution of the output at every time point itself will be a Gaussian process. Is that correct? It will be a normal distribution. I think that's correct. It will be a normal distribution. But it will be time dependent. So you will have time dependent inputs and time dependent outputs. This is quite computationally expensive, so we thought, can we do something simpler? Yes, we can. We can stick a curve through this kind of data, and we can then model the parameters of a curve. Like for quadratic, we can model the polynomial coefficients, or for a spline, we can model the spline coefficients, or whatever. So we did that. And you can see that for this kind of problem, we face this kind of decision making, that we have really noisy data, and we can stick a lot of different lines to it. So what do we do? Well, we tried a quadratic, because I wanted a curved line, and I made one with math. So that's the quadratic. Factor of safety terminates at 1, so we subtracted 1 from the factor of safety and worked with this data. And because we want the time to failure estimation within our modeling, we can actually rewrite this quadratic, including the time to failure. And the time to failure here becomes when the quadratic reaches the x-axis. So when y is 0, we get time to failure. except it's not that simple. Because you see that we have noise. We have some Gaussian noise, which looks innocent. But if you imagine a quadratic with a confidence interval going through it, then the noise will reach 0 quicker than the mean quadratic will. So that's a lot of pain. So we don't quite get time to failure for free, but we get something which is model time to failure, which is annoying, but there we go. We also need to constrain these coefficients to avoid convex curves. We don't want any U-shapes, we want only N shapes. So to do that kind of constraint, we need to rewrite the model to have these constraints, that the intercept has to be greater than 0, and the time to failure has to be greater than 0, and then the time to failure has to be the smallest positive that solves the deterministic part of y, which means that if you have an N-shaped curve crossing the axis, it has to be the second time to failure, and it has to be positive, not negative. So this constraint can be written out like that, whatever. You can see it in our publication if you're interested. Oh, no, you can't see it yet. You will be able to see it in our publication, hopefully. So anyway, we rewrote it. Now, this is when I both rejoice and cry, because it turned out that it had a lot of bugs. It had a lot of computational bugs. So to solve these computational bugs, my lovely supervisor at the time decided, let's code it in 3 languages. Woohoo! So we coded it in 3 languages, and it is painful, but it solved the problem. So we called it all in R. I used stan, base R, and JAGs. Yeah. It's fun, but it's also really painful. So there we go. And this is when you're really happy. So we have sort of, for these factor of safety runs, I have these MCMC traces, and the 3 colors of the MCMC traces, the red underneath is blue and the top is green. There are 3 different computational languages, and they agree. Oh, they agree. Eventually. And the blue lines were the truth. This was for synthetic data. The blue lines are the truth, so they agree. Great. So then we have some posterior fits, and we're looking at the red fits. So we have some overlaid red and green fits. So let's just look at the red bonds first. So red bonds is the quadratic model, and we have these different shapes of factor of safety, and for some of these factor of safety cases, the quadratic is really good, but for a factor of safety case 1, it's rubbish, because this is a very shallow earthwork, and it's really strong, and it looks like it's never going to deteriorate. So you actually have a compaction effect. So after you build the earthwork, once the ground compacts, you have a rare case that after compaction, it becomes stronger. So it actually took this earthwork some time to become even stronger than it was in the beginning. This is quite rare, and it's a numerical model example. In reality, this might not quite be the case, but here we go. So it does the job. It doesn't do it particularly well. So we have these green fits. Now, we thought, what can be better than 1 quadratic? Well, 2 quadratics. And you can, but there's different ways in which you can fuse 2 quadratics. You can fuse them sort of that they join. You can fuse them that they don't join. Or you can make a smooth transition. So we went with the smooth transition, and that's the fit using a smooth quadratic transition. And look out for the space, because I will hopefully publish it very soon. My poor postdoc is doing all of the slavery work. So this is where the bulk of my results end. We've trained a Gaussian process that estimates the relationships between time to failure and geometry. We gained a strong computational advantage over numerical models, and our future work, our current work is factor of safety curves, but with this smooth piecewise polynomial. And I'm also modeling yet another residual factor yet another deterioration curve, which is known as the residual factor, but whatever. And that's it from me.
Great, thanks, Alexander. Questions?
Is there a specific reason for the term that you use to define the sensitivity? Because they have different forms of sensitivity definitions. For example, some of them is probabilistic sensitivity. But the one that you introduced, I haven't seen before. Are you using it in your own setting, or is there any motivation behind that?
Yes, so it was, the sensitivity analysis is actually fully probabilistic, it's fully Bayesian. We used it because that was what seemed to be the golden standard in a bunch of different reasonable publications. So one of them is this book by Bobby Gramercy called Surrogates, which is a great book if you want to learn about Gaussian process. It's really, really good. And then another one are these two papers here. So the Saltelli paper is one of the pioneering papers really on sensitivity indices. And then the number 13 reference there is the Bayesian version of these sensitivity indices. And I think when you just look into a lazy search on Gaussian process sensitivity analysis, Bayesian, this is what comes up.
But it's the same sensitivity indices Steve was using in his
Yeah.
talk, yeah. In the middle.
I have a question about the first problem.
Yeah.
How does stationarity of the covariance function play a role there?
Yes, very good. You have to you have to make sure your process is stationary. And if it's not stationary, you should go with the dynamical Gaussian process. That's it. For our case, it's a fairly simple case. I'm sort of slightly ashamed to admit, but because of how many years I've spent looking at it. But it's a fairly simple case. The covariance function is fairly stationary. For this kind of a problem, it becomes more of a problem. But because we're using a very flexible mean function, the stationarity problem is not so difficult. Again, if that doesn't work, you have to use a dynamical Gaussian process.
How would you test this?
Well, we looked at some covariance properties a while back, but one of the main tests that we used validation on some holdout data, and that looked all right, and that was the main validation exercise.
What's a dynamical Gaussian process?
So a dynamical Gaussian process is instead of putting fixed inputs, you put time-varying inputs. So you have an order of magnitude more parameters, but it's trained on dynamical inputs. And this will affect the hyperparameters as well.
Good.
In the factorization curve, it looks like there's quite strong heteroscedastic noise
Yep.
going on.
Yep.
Is that something you tried to model? Or
Yep.
not?
So yes, yes, absolutely. So. What we're currently doing is that every one of these models has its own marginal variance, has its own noise variance. We didn't model noise-dependent, time-dependent noise variance yet, because it works quite well, because our current approach works quite well, and our flexible polynomial approach works quite well. And when you add heteroscedastic noise, you end up with another category of parameters which need to be optimized. So it's a choice between a gain in accuracy and a computational cost. In our case, the gain in accuracy is not dramatic. Therefore, we stick with an individual noise variance for each model. But this is something to look for in future. And if you use a dynamical Gaussian process, the problem kind of solves itself.
going to ask, you said how important it is to have a Bayesian treatment of the hyperparameters in your GP, and that's not something that's often done in machine learning.
No, no.
And I wonder if you tell a little bit more about why it's
Yes.
important and the costs.
Yes. So, well, it depends on how you've been evangelized. If you've been evangelized in Newcastle University, you are almost certainly Bayesian. In reality, it depends on how much data you have. It depends how strong your engineering knowledge is. So Bayesian inference is advantageous in two main scenarios. Scenario number one, you don't have a lot of data, or your data is rubbish, and you don't just want to rely on likelihood functions, you want to rely on some reliable knowledge. Reliable knowledge, there we go. Scenario number two, you have a big data set, but you still want to include engineering opinion, or medical opinion, or specialist opinion. Then you use Bayesian inference. In big data settings, when you have a lot of good data, Bayesian inference is not strictly necessary. But it is mainly useful when you can't evaluate a lot of models and you want to include engineering opinion. Okay. And in that case, you have to tune it quite well, otherwise you'll get rubbish.
And do the experts have expert opinion about the GP hyperparameters? That's distinct from their problem in some sense.
Typically, most often not. So it's your job to sit down with them and try to ask questions, and the answers you then have to formulate into prior distributions. You won't necessarily get prior distributions out of your meeting, but you might get information which can be then converted to prior distributions.
Jill?
Yeah, you mentioned doing transformations on the outputs.
Yeah.
And emulating transformed outputs.
Yeah.
I just wondered if you could say a bit more if you've got experience with that, because I have, I guess, dabbled with that. And
Yeah.
found that, okay, it fits nicely on your transform scale, but if you then want to go back to your original
Yeah.
scale, your errors just inflate crazy.
Yeah. Yes.
I was wondering what sort of experience you've had with that.
I can show you one plot if I may. I'll need to Google it, but I will show you one plot. So there we go. You have to make these kind of plots. So you have to have a validation set to begin with, and you have to try different transformations. So we have a square root transformation with Gaussian correlation function, Matern 3 over 2, Matern 5 over 2. We have a cubic root, we have a fourth root, and we have a log. So log is probably one of the most tempting things to use because it's so widespread. But here we have a problem that these high values become exponentially high on the transform the back scale. So you just have to look at your other transformations, and in our case, the square root worked quite well. So the square root, when you transform it back, then you still unfortunately get some errors in this high prediction region. This is sort of, in our case, this is close to where the climate data ends, so we don't have much information at that end, but it's not quite so bad. So you just have to try different things and compare them.
And how do you transform back to the original scale?
So for time...
Function, how do you then get an information?
No, it's much simpler than that. So for time to failure, you fit a Gaussian process, you have a region for which you want to make a prediction, you make a prediction of time to failure on the square root, and then you transform it, you just square it. You have to remove a few unpleasant things, like if you have slightly negative predictions, you have to make sure that they're positive. If you have strongly negative predictions, that you have to rethink what you're doing. Luckily, we didn't have that. We only had slightly negative predictions. So you have to square them back. But you make all of your predictions and you transform at the very, very last stage. When you have your prediction of the region you're interested in, and then you square it back.
Okay, so let's thank Alexander again. Thank you very much.